Good day once again, and welcome back to General Ship Knowledge. The General Ship Knowledge, the last part is what we are treating now, and after this, if you have any further questions, you can really bring it out. Before you are able to do, or before you qualify to take the General Ship Knowledge, you are supposed to do seamanship, but because you did not do seamanship, I'll give you a little brief idea of what really happens in the seamanship class. So I'll show you a little bit of anchor, mooring ropes, and the types of ropes that we have, the types of anchor. Though you are not going to be examining on the anchor and the ropes, but it is important you have a fair idea so that when you get to the next lecture, you'll be able to understand the concept very well. With the general ship knowledge, the calculation aspect is what is left. I want you to concentrate more on the Kaiser. The calculation aspect is what is currently left as we discussed. If you remember in our last submission, the diagram I sent you and the handout I sent you, I made you understand that we have kg plus gm will give us km. I want to show you here kg, the distance from k to g plus the distance from g to m will give us gm. That's this whole distance. It's just like you are moved from here and here plus this one will give us the distance from here to the top here. At the same time, when you have kb, the blue section, and then the bm, it will give us also the same km. So you can see if you are going with the red section, the kg and then the gm will give us km. At the same time, kb plus the bm will give us still km. So there are ways by which you can really calculate them, but know that the gm is the metacentric height. The gm is the metacentric height. Only the g is the metacenter. The G point is the metacenter, and that is considered to be the height of the ship. The G section is considered to be the height of the ship or the height of the block. And then you have the kg. The kg is the vertical height. The vertical height. So when you have gm, the gm here is the metacentric height. The m is considered to be something like an imaginary point where the vessel is assumed to be having its focus point. That's the pendulum point of it. So if you look at it very carefully, the height, the metacentric height is the gm, but the g is called the metacenter, and that is the this is the metacentric. So the metacentric height is this, and now we have the kg. From here to here is the vertical center of gravity, the vertical center of gravity, VCG. And we have the kb. Like I told you, the b is the center of buoyancy. And if you want the kb, the distance, it is just like half the draft of your vessel. For a block vessel, is half the height of your half the draft of your vessel, half the draft. But with the bm, that's from here, the b to m here, the bm is like a radius. It's just like a radius. It's just like when you are really having a pendulum or a ball and you are swinging it around, a ball in your hand, and you are standing on one of your leg and you are turning round, and the bm becomes that radius that by which from your chest to the ball, the center of the ball. So that is something like an assumption. So all that we are trying to say with the kb, you can really calculate from the diagram. With the kg, you can calculate from the diagram. The gm you can also calculate, but the bm has a special calculation. I will introduce you to it. You don't need to know about the bm, but I want you to have a fair idea that when your kb, or when your height is higher, when you have a ship and they have loaded at a very high height, then the possibility of being stable or unstable would determine on the cargo or the weight that is sunk below. and that is what we are going to concentrate our ideas on. So with this, I want you to focus more on this kg, gm, kb, bm. Let's get to the next slide. Let's check something. With the when you have the k is here, the b is here, and then the g is here, the m is here. Once the vessel is tilted, maybe in an examination when you are being asked to draw a vessel that is tilted to the port or the starboard, this vessel is tilted to the starboard side. When they say it is tilted to the port side, you slant it to the other side and show whether and show the k, this that's the keel, the center of buoyancy, the metacenter, and then the metacentric. You are also supposed to draw something like this to show. Let's consider this very diagram very well. You can see when the vessel was upright, the K will never change. Like I said, the B will tend to change because that is the water level. When it was full, the water level was covering this section. Look at the line. But when it was tilted down, the water level is taking this section. You can see there has been an increase here. And that increase will determine whether the ship will come back or it will not come back. And you can see the B has moved to B1 and the G here has shifted to another GZ because of the tilt. And this very GZ is called the righting moment, and that will determine whether the ship that has tilted to the starboard side will come back to the port side. The GZ will determine that, and that is what is called the righting moment. It's just like the pivot point, a pivot point. So it's like your seesaw. Once there is a weight here, the whole thing will come here. Once there is a weight here, to come here. So this will be will turn like a swinging moment for it. So this G is very, very important. So you need to understand it very well. When you consider, for example, a small angle of, let's say, 6 degrees, the GZ, if you want to calculate the GZ to know whether your ship is stable or unstable, the GZ will have GM sine the angle. So the GM and the GZ go hand in hand together, and that is what I want you to understand. Let's get to the calculation aspect. We have the KB, BM, the KB, the BM, the KM. I told you depends on the shape of the ship, the hull, whether you have it in a rectangular form or you have it in a curved or ship-shaped form. This form that you see here, this shape is not a rectangular. It is called ship shape. And I'll show you that of the rectangle. This is a typical rectangular shape, and this is a typical ship shape. So when you have a block, and if you want to calculate the KB, the KBM, the KM, all will depend on the shape of the hull. And now we know the shape, the hull. The KM provide in shape hydrostatic data. When you want to get the KM, normally, like I said, we will go through it for you to understand. With the KG and the GM, the KG and the GM, I repeat, with this KG and then the GM, it depends on the load. How you load your ship will make it, will be able to determine the KG and the GM. So KB, BM and KM depends on the shape of the ship, and they never changes. It is mostly constant. But with the KG and the GM, it depends on the load you are putting on the ship that will make the ship tilt in either direction. And that is what we are going to do. And from our diagram, you can see that GM is equal to KM minus KG. If we write it down, GM is equal to KM minus KG. Over here, they are saying GM is the same as KM. KM is here, this whole distance, minus KG. So if you know this whole distance here, and you know this very distance, then you can calculate this one. What it means is that if I know my KM to be 10, and my kg here to be, let's say, 6, then I know the remaining one is what? 4. That is simple basic calculation. So when your GM, when you do your calculation on a ship, sometimes the ship will come to the port and they will tell you the ship GM is this, the ship GM is that. What it means is that when your GM is more than 0, is a positive number, more than 0, then your ship is stable. When your GM is 0, your ship is in a neutrally stable. If you look at the video I sent you earlier on about the Indiaman explaining with the funnel, you realize that when it is 0, you just see how the ship will behave when you are in a neutral position. And when you have a negative GM, it means your ship is not stable at all. In any condition, it is likely to sink at any moment. And when, let's pick a typical example here. I want you to be very careful as you look at this very diagram very well. The diagram is much more important to me. This is a block that we want to establish the calculation. When look at this block, look at how it has been designed. It is lying on the flatter side. That's the largest side. So the breadth here is 4. The height is now 2, and then the length is 10. The length is 10. This block that we see here. So when we bring it in this condition, the breadth, that's the center of buoyancy. The center of buoyancy is considered to be this side. Okay, so half of it is considered to be the center of buoyancy. So that's where the breadth is supposed to be, the center of buoyancy. So if we go down back here, we are talking about where the water is covering. So you see your center of buoyancy to be the draft. Your draft, half of your draft is going to be the center of the buoyancy. Half here is going to be the center of buoyancy. Then just like I was telling you, look at the height of the block. The height of the block. The total height of the block is 2 meters. But when they dip this block, let's consider it to be an ice block. When they dip this ice block in the water, it is only 1 meter that is submerged in the water. So if we want the height of this, the center of buoyancy of the block, it means that is where the water is touching the block. And where the water is touching the block is 1 meter. So half of it, which is the center of buoyancy, is supposed to be 0.5. It is not the total block that is submerged in the water. The total length of the block is 2 meters here. Look at the cursor. But it is only 1 meter that the water is touching. And that 1 meter is considered to be the draft of the vessel. And the draft, half of the draft is the center of the buoyancy with this kind of design. And that is supposed to be 0.5. If we really want to take it carefully, the main height, the full height is supposed to be, that's the full height, which is 2, is supposed to be your kg, the whole height here. And that kg being the whole height will also go there. So let me bring you down for you to understand it very well. So when you come back here, you see the center of buoyancy. The height here was 1, and the center of it is considered to be 0.5. So it means 1 divided by 2 is going to be what? 0.5. If you look at the over here also, we are having the full height, which is 2. The full height, which is 2. That was inside here. That is the full height of the block, which is considered to be the main height of the ship. And that one also, if you want to calculate the kg, you have to divide the total height of the ship by 2. And that one is also giving us 1. This B section is the one that is submerged in the water, which was 1 divided by 2, giving you 0.5. and this 2 from the top here. And if you want to calculate the center of it, the center of this, it is considered to be also what? 1. 2, when you are considering the center of it, is going to be 1. And I want to show you how we calculate the km. I want to show you how we calculate the km. For you to get the BM. For you to get the BM, you go through this process. Remember, this is how the formula is, and you don't have to worry your head with it. But I want you to get the concept right. We have the initial metacenter being the L, the length times the breadth cube divided by 12. We remember the length, which was 10 from here. The length was 10 times the breadth cube. So 10 times 4 cube, which is here, divided by 12, you are getting this. And when you put this value inside here, the displacement, you have length times breadth times height. Length times breadth times height. So you have this. And the BM formula actually is this divided by this. And this is what we are getting. And all is taking effect because of the height that we are dealing with, and then the breadth. This is the breadth. Look at the breadth here, and this is the height here, which is 1 that we calculated. So at the end of it, we are going to get the BM to be 1.33. If we want to calculate GM based on the previous one, GM is going to be KB plus BM minus KG. KB we know is to be 0.5. BM we just calculated it, which is 1.33, and then the kg, which was 1 that we saw. This side 1, and 0.5 is this and that, and we just calculated this. When you do the calculation, you realize that you are going to get 0.83, and with 0.83, then your shape is considered to be stable because it is positive. Then the shape is considered to be stable. Let's come back to that's the same calculation I've done here. Let's come back to this block. The same block, we just tilted the block in a, I'll say, vertical position. The same block that we showed here. Look at the same block here. This same block, this 4, we have just turned it to make this breadth becomes the height now. And let's see how the calculation will be like. This same block, you see where the water level now is. This block, the height, half of it, which was where the water was, is now 2. Now the draft is now 2 instead of 1 because of the height, how we turn it. And now the length of it is still, the lengthwise is still 10, but the breadth has changed to become the height, which is 4, and now this breadth is now 2. So we will consider it in this way. Now the whole thing is 4 now, so half of it is going to give us 2. But unfortunately, when we sank this in the water, it was able to, the water level was able to make its level at 2. That is the draft of it. So when we are to put this back in the calculation, let's see how it will behave. You see now we have the length, and now the breadth has changed to be 2. You remember before the breadth was 4, but now the breadth is 2. When we put them in a calculation, we are getting the BM to be 0.17. So now our KB is now 1, our BM is now 0.17, and then the KG is now 2. When you do the calculation, you are getting minus or negative 0.83. So you realize that when the ship is having a very high height, the GM will reduce. You are likely to get a negative value, making your ship unstable. That is why whenever they are loading, we tell them that they should put the heavy cargo below, the very heavy cargo below, so that the ship can go more into the water. Once it goes more into the water, it becomes much more stable. The height on it reduces. But when you have a higher freeboard, your reserve buoyancy reduces and you are likely to sink your vessel. So this is just by the way for you to understand how the calculation of the GM goes. But under normal circumstance, I want you to come back with any questions that you have. Then once we are settled and I don't receive any further question by Monday, I'll send you the guidelines on how you should answer the questions on the online questions that we have set for you to do it in the house. And we will try to see if it is possible for us to also do one more exams so that we will add up to what is left. Otherwise, I will be forced to mark your exams over 70, which will affect you greatly. So thank you very much and have a wonderful time.